My video response part 2 of the continuum hypothesis is true response series. Okay, so last couple of videos, last couple of days, I acknowledged I did some research, and it turns out that the set of rational numbers is, equivalent to that of the natural numbers. As you said, Cantor proved. Did not know that before. That's a new piece of information, which is, good to know. So that is, uh, recap of last time. But today I wanted to talk more. It's instead of just talking about the debate whether it's true or false, because really, I mean, everyone is going to have their views on the continuum hypothesis. It's again, as in the previous video, not proven or disproven in Zermelo-Fraenkel set theory. Maybe, I guess, like I said, in second order logic, axioms there could definitely be defined. Okay, so this video I am titling the good, the bad, and the primes, because recently I came up with the idea: how can continuum hypothesis be applied to number theory? Because that's, instead of why is it necessary to just be pure mathematics? Quite frankly, I think pure mathematics can be studied for its own right, but to really have tangible use, I would definitely try to apply it. And I found an application, well, indirect, not completely direct, but indirect way to look at things a little differently from the standpoint of the continuum hypothesis. Okay, so basically, I wrote down some number theory topics. I'm not sure if how many of you guys have ever studied number theory, but let's start with right here. A mod Aleph not. Now, how exactly do we think of this? Because if you've ever done modular arithmetic kind of goes like this. It's sort of like the numbers wrap around. Like, let's take a clock, for example. The mod would be 12, because in non-military time, after 12, the numbers they loop around. Like, for example, if I have 11 mod 12, it's going to be 11. But if I have if I have 14, it's going to be 14 mod 2. That would be, 14 mod 12. The answer to that would be 2. And then 16 mod 12 would be 4. I mean, you sort of, catch on to it pretty quickly. Now, what about if we wanted to, what if it's mod Aleph not? What exactly, when exactly do the numbers loop around? Now, this is actually, I would definitely argue this is also undefined, because, once we get to infinity, we can't really loop, first of all, infinity can't really be reached. So essentially, there is no wrapping around like in the typical modular arithmetic or modular exponentiation operations. And then the same I would also argue for the LF1, or the cardinality of the reals. It's for the exact same reason. It's infinite and we'll never really quite get there. Now, how can this be applied? Well, again, let's look at some. It's been long conjectured for I think at least hundreds of years, because prime number theory has been studied for the longest time. I mean, numbers have been around. The study of numbers has been around since the Egyptians, and even probably before that. But so let's look at something called twin primes. Now, twin primes are essentially quite simply, there are two primes, and the distance between them is equal to 2. 11 and 13, 13 and 15, 17 and 19 are some typical examples. I mean, 5 and 7 are also twin primes. So it's been conjectured, and there are infinitely many. You can say that infinitely many twin primes, because technically, when you think of primes, like what would the cardinality of the primes be? Well, actually, it's unknown, because it's not really known how many primes are out there. It's conjectured to be an infinite amount of primes, simply because of the fact that there's an infinite amount of numbers. So why can't there be an infinite amount of primes? And some pretty large prime numbers have been found with the aid of computers and very efficient, actually supercomputers, very efficient architectures to make them find these very, very large prime numbers. And they're used extensively in cryptography, for encryption schemes. Like modular exponentiation is conjectured to be a one-way function. If you guys watch my theory of computation video series, this will make a lot more sense if you understand a little bit of computer science, how it's how number theory is used. But in addition to all of this, is continuum hypothesis, can it be used to prove theorems in number theory, and suggest that there are infinitely many primes because of the fact that since numbers keep going and there's no definitive limit to the primes, and why would they stop all of a sudden? There's no, I mean, again, it's not quite as simple as that, because there's no from one prime to the next, to the next, to the next. There's no like general formula to follow, because if there was a detectable pattern in the prime numbers from 3 all the way down to the highest prime known, then prime number theory would be way more advanced, and we'll be talking about something else in this video. But nonetheless, I would imagine in number theory to use continuum hypothesis to solve some conjectures. And one of the ideas I came up with was such as a way to go about doing it, like something called a Cullen number, which is right here. A Cullen number is essentially a number x that is n times 2 to the n plus 1. That is a Cullen number, and such that x is a member of the natural numbers. Now, since the Cullen numbers are a subset of the natural numbers, because in which they're a subset of the natural numbers, then and a subset of an infinite set is an infinite set. So that sort of that sort of implies there, right on the spot, that they're infinitely many Cullen numbers. But what about the other ones? I mean, there's also something called hyperreal numbers, which I'll get to in a minute. But yeah, to reaffirm what CH is was saying, there is actually if you guys again if you guys ever see my video on partial and total functions, there's actually a one-to-one mapping from the natural numbers to the rational numbers. So it is essentially isomorphic or equal to, just as Gay-Cantor proved. So yeah, that is, I guess, some ideas, but there's, again, also the hyperreal numbers. Now, what are hyperreal numbers? Hyperreal numbers are a little abstract and somewhat difficult to define, but essentially they're an extension of the real numbers. Something a little different. Now, how exactly does it play into the how does it exactly play into the continuum hypothesis? And, well, there's a little algebraic operation to show that the cardinality of the real numbers is the highest cardinality there is. Hyper real numbers, the cardinality of hyper real numbers, again, contrary to intuition, just like the set of integers is to natural numbers, the cardinality of the hyper reals is equivalent to that of the real number set. Again, if you study continuum hypothesis, this may not be surprised. It may make sense, but for the guys who haven't studied it, this is counterintuitive, as continuum hypothesis has proven to be. So the way it works is, you have we have two. Let me fix the notebook there. All right, so we have 2 to the left naught raised to the left naught power equals 2 left 2 subscript 0, which therefore implies 2 to the left naught. Like, look at it's essentially the exact same thing, because a left naught is just the highest go. I mean, it's all abstract. I mean, it's all some ideas into how to go about doing it. But yeah, from the standpoint of I guess number theory, continuum hypothesis seems to be quite a help. And again, using continuum hypothesis, you can find some primes or other numbers and use them for encryption schemes. Discrete logarithm problem is based also similar to the modular exponentiation problem. I mean, there's a lot of stuff that can be said about continuum hypothesis. I mean, it's not really something that can be completely covered in a couple about 10, 15 minutes. It just takes a while. But so continuum hypothesis, do you really look at it? I mean, it has aspects that can make total sense, and then some aspects that don't make total sense. But that's just counterintuition. But at the same time, counterintuition does not mean it's wrong. Just to the simple steps. Look at quantum mechanics. Back when quantum mechanics formulated the idea of a basically the object of not being precisely where it is very counterintuitive. Matter being a particle and a wave. In addition to particles, tunnel through potential barriers. Like, for example, if you're on a roller coaster, or any kind of object, and your potential barrier is something like going up.